Welcome to this explainer. Have you ever looked at a massive industrial pipeline, or honestly, even just the plumbing sitting right under your kitchen sink, and thought of it as just a static, boring piece of metal or plastic? Well, today, we are going to completely shatter that illusion, because underneath that seemingly calm, motionless exterior, pipes are actually dynamic battlefields of physics. They are constantly fighting against invisible forces that want to rip them apart.
To really wrap our heads around this, let's totally shift our perspective. I want you to imagine, just for a moment, that you are a highly pressurized drop of fluid rushing inside one of these pipes. When you're inside that system, it isn't peaceful, it is violent. You and millions of other fluid particles are crashing against the walls, pushing, pulling, and twisting the very structure that contains you. So what forces are actually keeping that metal from violently ripping apart? What really makes a pipe burst?
Okay, let's dive right into our roadmap for today. We'll be looking at 1. Pressure from within, 2. The tug of war, 3. Environmental forces, and 4. The master equation. These are the fundamental stresses engineers have to calculate to keep our infrastructure completely safe. We're going to break down exactly how internal pressure, axial forces, and environmental factors all act simultaneously on a single pipe. By the end of this explainer, we'll be able to read these overlapping equations exactly like expert engineers do, mapping them straight onto the real physical world.
Section 1. Pressure from within. Let's start from the inside out.
The very first force we encounter is called hoop stress. Think about how a tight belt feels after a massive Thanksgiving dinner. That outward pushing force, that's hoop stress. It's the fluid inside pushing outward in all directions, trying to split the pipe straight down the middle, acting entirely along the circumference.
You can actually visualize this with those blue arrows labeled sigma H. They show this outward expanding pressure perfectly. We can clearly see how the fluid inside is constantly trying to stretch the pipe's diameter wider and wider, which means the pipe material has to continuously fight back just to hold its shape.
Translating the math here into plain English, hoop stress goes up when the internal pressure and the diameter of the pipe increase. Makes sense, right? A wider pipe literally has more surface area for the fluid to push against. But if you look at the denominator, we can reduce this stress by making the pipe wall thicker. It's this fascinating direct balancing act between the fluid's pressure and the metal's thickness.
But hoop stress isn't flying solo here. Still looking from the inside, we've got radial stress. If hoop stress is the fluid trying to stretch the pipe like a balloon, radial stress is the literal squeezing force traveling straight through the thickness of the pipe wall itself. It moves right from the inside directly to the outside.
And this is such a brilliant contrast. The inner wall is taking the absolute brutal brunt of that internal pressure, which is why the stress there is roughly equal to -P, representing that really high compressive force. But as that force travels through the thickness of the metal, it completely dissipates. By the time you reach the outer wall, it experiences practically zero radial stress. The inside is fighting for its life, while the outside barely feels the thing.
Section 2. The tug of war. Let's move along the length of the pipe. Enter longitudinal stress. I want you to think of this exactly like a massive, invisible tug of war taking place. Whether it's the sheer weight of the pipe hanging there, thermal expansion as super hot fluids pass through, or the pressure hitting closed ends and valves, there are massive forces constantly trying to stretch the pipe apart from end to end. Those red arrows, labeled FL, demonstrate exactly this. That's the internal layers of the metal being aggressively pulled in the axial direction. So the pipe isn't just trying to burst open horizontally, it's literally being stretched vertically or longitudinally as well. The math for this is pretty straightforward. This stress is calculated by taking the total pulling force, that's FL, and dividing it by the pipe's cross-sectional area, A. More force obviously means more stretching, but a pipe with more metal, meaning a larger cross-sectional area, can better resist that stretch. It's a pure test of the material's tensile strength. Section 3. Environmental forces. Now we're zooming out entirely.
We need to see what happens when the outside environment starts physically manipulating the whole piping system, because pipes don't just float in a void. This brings us to shear stress. Unlike the pushing and pulling we just covered, shear stress happens when forces push parallel to a surface. It's essentially the environment trying to slide layers of the pipe past one another, almost like sliding the top half of a deck of cards off the bottom half.
This usually happens in two main ways. First is through torsion, which is a twisting force. Imagine wringing out a wet towel, but you're doing it to industrial steel. The second is transverse shear. That's a direct, cutting force pushing straight up or down across the pipe, and it's often caused by the sheer weight of the pipe resting heavily on a support beam.
And closely related to that weight is bending stress. This is exactly like the forces at play when you snap a twig over your knee. Bending moments cause the pipe to physically sag or bow in the middle, whether it's bridging a big gap between two supports or just holding the heavy weight of the fluid inside.
When a downward force acts right on the middle of a suspended pipe, it creates this fascinating duality. The top half of the pipe gets squeezed together, that is, compression. But the bottom half of the pipe is being stretched apart, and that's tension. The metal is literally fighting two completely different battles depending on whether it's above or below the center line.
To figure out this bending stress, represented by sigma b, engineers multiply the bending moment by the distance from that neutral center axis. Then they divide it by I, which is the pipe's unique second moment of area. In plain terms, this proves mathematically that the shape and thickness of the pipe dictate exactly how well it can resist sagging under immense weight.
Section 4. The master equation.
We've looked at the individual battles, the expanding, the stretching, the twisting, and the bending. But now we have to look at the entire war zone. It is just mind-blowing to realize that a real-world pipe never experiences just one of these forces in isolation. It faces hoop stress trying to burst it, radial stress squeezing its walls, longitudinal stress pulling it apart, shear stress twisting it, and bending stress bowing it, all at exactly the same time every single second of the day.
It literally is a dynamic battlefield of physics, hidden right in plain sight. Engineers have to miraculously balance every single one of these formulas simultaneously. They have to select the perfect material, the exact wall thickness, and the absolute optimal support structures to ensure that all these overlapping stresses never exceed the breaking point of the metal. That's how we prevent catastrophic failures in our cities and factories.
It really makes you look at the built world a little differently, doesn't it? So I want to leave you with this thought. Next time you pass a massive industrial pipeline, a sprawling refinery, or honestly, even just your home's humble plumbing, pause for a second and ask yourself, what intense, invisible battles are raging inside that metal right now? Thank you for joining me on this explainer to uncover the hidden physics that make our modern life possible. Until next time, stay curious.